All right, let's get right into it. We're going to cut through the noise and focus on the four fundamental types of chemical structures. My goal here is to break them down so you can actually understand and, remember them. Let's jump in.
So here's the plan. We're going to tackle these four categories one by one. We'll start with giant ionic, then move to simple covalent, then giant covalent, and we'll wrap up with giant metallic. By the end, you'll see how pretty much everything is held together at the atomic level.
First up, giant ionic structures. The name itself is a pretty big clue, right? We're talking about something massive, and it's all about ions. So let's take a look at the powerful forces that create these really cool, orderly patterns. So what's the most important thing to remember here? It's all about attraction. You've got your positive ions and your negative ions. And that powerful electrostatic force, that same thing that makes a balloon stick to the wall, is pulling these oppositely charged ions together into this super-packed, repeating 3D grid. And that's what we call a giant ionic lattice. And here is the classic example everyone uses. Good old table salt sodium chloride. Just look at how each positive sodium ion is completely surrounded by negative chloride ions, and every chloride is surrounded by sodiums. This is what creates that strong, stable, three-dimensional structure that just goes on and on and on. Now, these properties, they come directly from that strong lattice structure. You need a ton of energy to break all those attractions, which is why they have such high melting and boiling points. And conductivity? Well, the ions have to be free to move around to carry a charge, and that can only happen when you melt the substance or dissolve it in water. As a solid, those ions are just locked in place. And finally, they're brittle, which seems kind of weird for something so strong, right? Well, this shows you exactly why. If you smack an ionic crystal, you can actually force the layers of ions to slide just a tiny bit. But suddenly, you've got positive ions lined up next to other positive ions and negative next to negative. They instantly repel each other with a huge amount of force, and the whole crystal just shatters. So how can we predict how strong these bonds are? We use something called Coulomb's law. Now, it sounds complicated, but the takeaway is actually really simple. The bigger the charges on the ions, the stronger the attraction. And the smaller the ions are, which means the closer they can snuggle up to each other, the stronger that attraction is. So more charge plus less distance equals a much, much stronger bond. Okay, let's put that to the test. How would you rank these? Well, first things first, look at the charges. Aluminum oxide has +3 and -2 ions. Whoa. Magnesium fluoride has +2 and -1. The lithium compounds are just +1 and -1. So right away, you know aluminum oxide is going to be the strongest, then magnesium fluoride. Now, what about lithium chloride and lithium iodide? We look at size. The iodide ion is way bigger than the chloride ion, so the distance between the ions is greater, making the bond weaker. So the final order from highest melting point to lowest is Al2O3, then MgF2, then LiCl, and finally LiI. Okay, on to our second category. We're making a big shift here from these giant lattices to something much, much smaller. Simple covalent structures. Think individual, separate molecules. This right here, this is the single most important idea for this entire category. You have these really strong covalent bonds inside the molecule, holding the atoms together. That's intramolecular. But the forces between one molecule and its neighbor, those are super weak intermolecular forces. It's a huge difference. When you boil water, you're not breaking the strong bonds inside the H2O molecule. You're just overcoming the weak little attractions between all the different water molecules. And that one idea explains all of their properties. Low melting and boiling points? Of course. It takes barely any energy to overcome those weak forces between molecules. They don't conduct electricity because there are no free-moving charged particles at all. And for solubility, it's all about that rule, like dissolves like. Polar stuff dissolves in polar stuff, nonpolar in nonpolar. Simple as that. Now, the strength of the bonds inside these molecules still matters, and it follows a really logical pattern. A triple bond is stronger than a double, and a double is stronger than a single. And just like we saw with ionic bonds, smaller atoms that can get closer together tend to form stronger bonds. All right, time for our third category. We're taking the covalent idea and just scaling it up, way up. Forget about those little separate molecules. Now we're talking about a massive, continuous network of atoms. So here's the deal. There are no individual molecules at all. Instead, every single atom is linked to its neighbors by super strong covalent bonds, forming one gigantic structure. You can think of the entire crystal as basically being one single enormous molecule.
And this is just the perfect illustration of how structure is everything. On the left, you've got diamond. Every carbon atom is bonded to 4 others in this incredibly rigid 3D shape. Then on the right, you have graphite. Here, the carbon atoms are bonded in these flat 2D sheets that look like chicken wire. The layers are stacked, but the connections between them are really weak, so they can slide right past each other.
So you can probably guess the properties, right? If you want to melt diamond, you have to break an insane number of those super strong covalent bonds. That takes a massive amount of energy, which means a crazy high melting point. That network also makes them extremely hard and insoluble. And normally, the electrodes are all locked into bonds, so they can't conduct electricity. But as we saw, there is one very big exception.
So why is graphite the odd one out? In those flat sheets, each carbon atom is only bonded to 3 others. That leaves 1 electron from every atom that's, well, kind of free to roam. These delocalized electrons form a cloud that spreads out over the entire sheet. And because they're mobile, they can carry an electric current. It's the whole reason graphite conducts electricity and diamond doesn't.
Okay, let's hit our 4th and final category, giant metallic structures. This is what makes metals, well, metals. And it all comes down to a really cool idea called the sea of electrons. Okay, try to picture this in your head. You have a neat, orderly grid of positive metal ions. Now imagine their outer electrons have all left home and are just swimming freely between all these positive ions, forming this mobile sea of negative charge. The metallic bond is the powerful attraction between all those positive ions and this negative sea of electrons, holding everything together. This model just perfectly explains why metals behave the way they do. They conduct electricity because that sea of electrons is full of mobile charges, ready to go. They have high melting points because of the strong attraction between the ions and the electron sea. And what's really cool is their malleability. Unlike an ionic crystal, if you hit a metal, the layers of ions can just slide past each other, and the electron sea just flows around them, keeping the whole thing together. That's why they bend instead of shattering.
So what makes a metallic bond stronger or weaker? Surprise, surprise, it's basically Coulomb's law again. The bigger the charge on the metal ion, say a +2 magnesium versus a +1 potassium, and the smaller that ion is, the stronger the electrostatic pull on that electron sea. And that means a stronger bond and a higher melting point. All right, one last practice run. We've got potassium, calcium, magnesium, and rubidium. First, check the charges. Calcium and magnesium are +2, potassium and rubidium are +1, so you know Ca and Mg are going to be higher. Now let's compare the +1 ions. Rubidium is bigger than potassium, so its bond is weaker. Then for the +2 ions, magnesium is smaller than calcium, so its bond is stronger. So the final order, from lowest to highest melting point, is rubidium, then potassium, then calcium, and at the top, magnesium.
And there you have it, the 4 fundamental structures: giant ionic, simple covalent, giant covalent, and giant metallic. Each one has a totally unique way of bonding that explains all of its properties. The last thing I want to leave you with is this. Now that you get how these things are built, think about how that defines our entire world. Why do we use copper for wires, diamond for cutting tools, and steel for skyscrapers? It all comes back to these 4 structures.